Okay, remember this thing? That mysterious chart of boxes from chemistry class? Of course, it's the periodic table. It lists all the known elements, like hydrogen, gold, calcium, aluminum, and even down here, Einsteinium. And what makes an element unique is the number of protons each atom contains. We call that its atomic number. The table starts up here at 1 and keeps going and going and going, but way down here, it just stops. What's up with that? Why can't we just add more protons to an atom and build new elements? Well, correspondent Carla Wall has found some folks who spent their lives trying to do just that.
Every atom in the universe was born in fire. Oxygen, iron, neon, copper, carbon. The fundamental building blocks that make up all matter, all things, were created with immense heat and pressure. By the Big Bang, stars, or sometimes by scientists like Ken Moody.
I don't feel very stellar, I guess.
He does, however, rise before the sun each morning and gets to work by 5, 7 days a week.
That's the way it is.
He's a nuclear chemist whose passion is filling in the blanks at the upper reaches of the periodic table.
Pop quiz.
The chart of elements.
Number 44.
Ruthenium.
Oh, very good. 109.
Meitnerium.
Very good. 114.
Unnamed at this point. You're not going to trick me.
The trick, as Ken sees it, is to be the one to name 114, which he's been on a quest to discover for more than 2 decades.
We tend to call these things discovery experiments, but we're really producing them. It's an act of creation.
Creating them with atomic colliders, quantum calculation, and something passed on to him by his mentor, Dr. Glenn Seaborg.
He was a big believer in those little 35-millimeter slides, and he'd take a graduate student to run the projector for him.
One of those students was none other than Ken Moody. That's a younger Ken there. For 30 years, Ken has held on to this particular slide. Seaborg's map, a mythical place the elements of the periodic table inhabit. And it's here where our story begins.
Where uranium and thorium dwell, the end of the nuclei that exist in nature.
Number 92, uranium, is the last of the naturally occurring elements. This is as far as the stars got. But Glenn Seaborg thought he could pick up where the stars left off, actually creating elements, and he did. Marching up the periodic table, creating elements 94, 95, 96, 97, 98, 101, and 102. He won a Nobel Prize for his pioneering work and created more elements than any human ever had. And then he could go no further.
Even Seaborg ran out. The process by which he was making these, he and his whole large team by this point, that way of trying to add in more protons to a nucleus, that route finally dried up.
David Kaiser teaches the history of science at MIT.
What Seaborg had been able to do, and many colleagues by this point, was sort of go step by step, add in one new nucleus at a time by just going literally baby steps.
How exactly do you take baby steps? Let's start at the beginning. We'll take a trip and fly into an atom, past the electrons, into the nucleus. In a science where you never see what you're working with, a lot is left to the imagination. So first, let's meet some protons. For our purposes, represented by these guys.
All positively charged, and we all remember from science class in high school that 2 positive charges repel one another.
With this repulsion, how do any of the elements stay together?
The protons feel a different sort of force as well at the same time. It's a different origin, a different type of force between them, and that's a specifically nuclear force. It's called the strong force.
We'll show this as a bungee cord.
And that really is how this force behaves. If they try to pull apart, it'll pull them back together. It's an attractive, coming together sort of force. But like a bungee cord, it only works over a certain distance. If you try to stretch it too far, that cord will break.
That repulsive force wins.
And that's where this guy comes in.
Hello.
He is a neutron.
I went to school with an awful lot of neutrons. This is a fellow who comes equipped with bungee cords like the proton.
But unlike the proton, he has no charge, no inclination to push anything away. He just sort of sits there, neutrally, His bungee cord does the work. So, throw him in between a pair of struggling protons, hook up his bungee too.
The neutron provides some remediation of the hostility of the protons, and they can survive.
Up to a point. By the time he got to element 102 with 102 protons in the nucleus, Seaborg began having problems.
Even if you add in more bungees, they might keep this cluster together here, they might keep that cluster together there, but keeping the whole big thing together, that no longer is going to work. The pushing away force starts to win.
And there was another problem. Seaborg found the more protons he added, the shorter the atom survived. From billions of years down to thousands, days, hours, minutes.
Even much less. Sometimes thousandths of a second. If you're lucky, often it's millionths of a second. So these things will fall apart literally in less than a blink of an eye.
Seaborg came to see himself surrounded by a cruel and inhospitable ocean that tore his atoms apart. He called it a sea of instability.
The sea that they didn't know if they could cross or not. That's what was inspiring and really teasing or pushing Seaborg, and in fact many of his students and colleagues, to see could they go beyond this end of the known world? Could they go beyond where this peninsula seemed to stop?
Then in the mid-1950s, theorists presented a radical new concept of the nucleus.
There became lots of evidence to show there's a tremendous amount of very stringent, strict ordering that goes on inside the nucleus.
We're used to looking at diagrams where the nucleus is shown as a little ball with a plus sign in it, and the electrons travel in rings which are well-defined orbits. The nucleus is the same way. The protons and the neutrons can be treated as forming structures. You can think of it as rings.
And so in fact there are these configurations where the protons can line up in a special way in these sort of ring structures that will give a greater degree of stability to the nucleus as a whole than if there had been in some other random or messed up order. And same thing happens with the neutrons.
Just like the electrons that orbit the nucleus, the stability of the nucleus depends on how full these rings are. When you have just the right number of protons,
That is a configuration which we consider magic.
and just the right number of neutrons as well, that's called doubly magic.
So what's so magical about that? These magical numbers of protons or neutrons are such that you have the maximum stability.
That is a very strong nuclear configuration.
Theory predicts that element 114 should have this kind of doubly magic nucleus. So it should be, despite its tremendous size, incredibly stable. Seaborg would have to change his approach.
Don't add one particle at a time, add 20 particles at a time, add 40. And so that's like slingshotting over that sea instead of trying to march across it step by step.
And Glenn saw this as a giant leap across a sea of instability of things that you couldn't make to an island sticking up out here.
An island of stability.
So that was what was motivating Seaborg. Could you jump this inhospitable sea to get to this, what he hoped would be a magic island, an island of stability? Way up here, where you have all the way up to 114 protons and 184 neutrons. That was the next spot, they thought, where you'd have this sort of magic stability, both a filled ring of protons and, crucially, a filled ring of neutrons.
Where these huge atoms might last long enough to hold in your hand, to look at. Something new in the universe.
How badly did he want to get to the island of stability?
He wanted it bad. He really did.
And tried for 30 years?
Yes, basically yes. We all thought that if he could discover super heavy elements, that we could get him a second Nobel Prize.
So how would Ken realize this dream and leap to element 114? Well, plutonium has 94 protons. Calcium has 20 protons. Add them together and voila, 114. But how exactly do you add atoms together?
You have to accelerate them at one another very, very fast. so
You're
that they
throwing
can-
them at each
you're
other.
Throwing them at each other. You can almost think of it as bowling. Each calcium ion is a bowling ball. And as the calcium approaches the target, it sees a set of plutonium pins. And there are an awful lot of gutter balls. The calcium just misses the pins completely. We will put somewhere between 10 to the 18th and 10 to the 19th balls through a target. 10 billion billion. there's that one sweet spot there. If the calcium hits the thing, you get the element 114 strike. The calcium and the plutonium fuse, and you have an element 114 that survives.
Did they make it to the island of stability? Almost, but not quite. In 1998, Moody's team, in cooperation with Russian scientists, was able to bowl the magic number of 114 protons, but fell short of the 184 neutrons needed to achieve that double magic. In other words, while they still hadn't landed on the island of stability, they were this close, just at its shores, and that was no small feat.
I said to myself, I have to call Professor Seaborg and I have to talk to him. One of the great disappointments in my life was we couldn't have done that experiment 2 months earlier. He never knew about the result. He had had his stroke. He passed away a few weeks later.
Never knowing his magical island had been sighted. With Seaborg gone, Moody now continues the hunt for element 114's missing neutrons.
We're 10 neutrons short of where the maximum effect should be.
And those neutrons mean everything.
Big difference. The difference between existing and not existing.
Those neutrons may hold the answer to how long it might last.
Whether we're dealing with something that's very long-lived, like on the order of the age of the universe, or whether we're dealing with something that's minutes or hours.
But even minutes or hours is long enough to see, touch, and study.
I mean, a chemist's eyes light up because you can start thinking about doing all the chemistry experiments in the world.
Experiments to reveal what its properties might be. Perhaps a material with uses we haven't even dreamed of.
Maybe a ball of gas, actually. There are some predictions that think that it's actually a gas.
It could be a really heavy metal.
The periodic table says it should be a heavy cousin to lead and tin.
That would be very exciting because then we could prove that periodicity is, the chemical properties continue to extrapolate as you expect from the periodic table.
We would learn a tremendous amount of just basic nuclear physics. There's still these questions that we just can't figure out until we can make the stuff, study it, and ask these questions in the laboratory.
One thing is certain, we will have something the stars did not leave behind. If only we can get to that magic island.
We think it's there. Can we get there? Can we plant our flag in the sand?
Maybe Ken Moody can.
That's the mystery of the island of stability.
There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.